Let me begin our recording and begin the lecture. All right, welcome back after the relatively long break and quiz 2 in the middle. I assume everything is flush from your cache. Okay, cool. So what did we cover last Tuesday? ISA. Like instruction. Wait, what? I kind of, well, so we went over ISA, we went over risk versus CISC, we went over different ISA design that would be complex instruction versus I just want to support simple instruction and have a lot of remaining transistor for fancy things in the micro architecture, right? Please, first of all, recall that ISA is what is visible to the programmer. This is kind of like the last level before you go into the depth of hell. No, I'm joking. It's not hell. It's nice, right? It's nice down there. But this is the last level as a programmer that you guys can access. You can program in assembly. All right, you can program in assembly in a general purpose computer. We are not going to talk about things like FPGA where you both program the software and the hardware. We're not talking about that. Right now, let's assume you have the ISA, right? We call this architectural state. Why do we need that? How many of you guys use a debugger in Visual Studio Code or IntelliJ or anything? Imagine anyone wondering, how can I pause in the middle of executing a program? So the first question is, how do I pause? And that question should right now be relatively simple for you guys, right? How do I pause from it? Yeah, well, send the signal, hey, stop running at this line and that line. How do I tell what line to pause? I mark it, right? And that marker is tagged with the address of that instruction. So when what reads that instruction, the program counter, right? If the program counter happens to go to that instruction, I can pause. Then what do you do in the debugging mode? Let's say you pause, what do you do next? Resume and play. So what do you do? Except pausing and running. How many of you print out or like observe what are the, yeah, you look at the value, right? What's in each of these things, each of the variable you define. Those are architectural states. Those are architectural states, things seen by the programmer. Things like number of register, you know that. That's EAX, EBX, or x86, right? You learn from system skill. For the purpose of this class, we just call R0, R1, R2, R3. Program counter, instruction pointer, you can access these. You can also access the memory from the programmer point of view, right? Programmer can directly see and handle these values. What are some of the structure we've seen so far, including system skill, where you cannot access and control? What's the set of lectures that come after the assembly and system skill? Last module. Caching. Can I directly manage the cache? No. It basically would follow automatically, right, with some policy. And assuming you program it in a cache-friendly way, your program gets faster. Why do we design it this way? It makes your life simple as a programmer because you don't have to worry about what do I put in the cache, right? Are there designs with programmable cache? Yes. Sometimes we call this a scratch pad. They are available in, for example, the GPU. If you know your program well enough, you can pin some of the data, say, hey, put that in the cache because I know I need it. That usually is when you need performance, right? Yeah. So these are the states that are not visible to the programmer, and we call this microarchitectural state. There's no way for the programmer to access, at least in theory. In practice, there are ways to manipulate these things. And usually that comes as a result of someone trying to attack your hardware. Sometimes we call this side channel attack that can kind of hack and see into like, hey, these are the data in the cache. But the assumption is you're not supposed to see these things. All right. The assumption is these are things that are happening in hardware designed so that your computer are faster. These are, for example, the value in the cache block or the intermediate value of something that are inside the pipeline when you try to execute one instruction. We'll learn a little bit more on Thursday what is pipelining. All right. Now that we have the ISA, right? Now that we have the ISA, we have the method to give the computer the command. So what's left? Have we built the computer yet? No. So from now on, we're just building that computer to listen to the command and execute it. All right. So that's the hardware. How to connect all the circuits together and how to machine actually understand this method, and that's your project 3. Right? With this bit stream from your executable, how do you run the program? And the way you run it is, let's assume that right now you do debugging on your program, you pause. You are going to be at one of the architectural states, something here. Right before you resume the execution, that's your state, right? Let's say you're in the 5th line in your main function. Let's say this is like 5th line in your main function. And then the next thing is the next assembly code that you see, right? So what does the computer do? Consume that next instruction and update the state, right? So basically the whole thing is the next step, I process the instruction so that I can update my architectural state from AS1 to AS2. Any questions so far? So in a high level, it's as simple as this. I keep consuming instructions so that my register file get updated, my memory get updated, and the cache is updated, and all these things are updated. Then the architectural states are things that are visible to the programmer, so that the programmer see that your program are running, right? And at the end of your program, so that the program see your results in the memory, right? So what do we expect? Basically, the ISA that we learned from last week, basically that's a specification on what does architecture set looks like given the instruction. If I have state 1 and I have the instruction add something, 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 what should the result look like? What should be the next state? And that's it. That's the ISA, right? So from the programmer point of view, how many people think of computer this way? I have a series of assembly code, right? And I will consume line by line by line by line. So that should be the default view by the programmer, right? And that's quite easy to kind of basically visualize and easy enough to program ish, right? Okay. How many people so far in your 3rd year college think that sometimes for a program can be super complex already? Yeah, so our job as a hardware designer is try to limit the complexity so that you don't have to worry too much, because in that case, you program and assume that the program run line by line by line by line, except when you deal with functional program, but we're gonna talk about that later. All right. And then microarchitecture would implement how I get from the initial state to the next state. So the ISA dictates how the final state looks like. The microarchitecture dictates how do I get there. It's the hardware that gets you there. So there can, for example, let's say you want to do a division. Division can be a complex operation, right? So how do I finish a division might involve multiple steps. Or even think of multiply. Multiply is going to be more complicated than adding, right? So to finish a multiply instruction, you might need to follow like 5 more steps compared to an add. And how you get there is my design choice. I will just pick a design and that's it, right? The programmer will not see the design. You can read the specification and see how fast my chip is. But my intention is don't modify these things. Just use it. So you can do AS1 to AS2 in one single clock cycle, or I can do AS1 to some temp state that the programmer never see it. The programmer will only see AS1 and AS2, but internally, you would have to progress, for example, 3 cycles to finish from AS1 to AS2. All right. So what are the trade-offs? So let me ask you a quick question, all right? If I have to make sure that every single instruction in my ISA get to AS2 in one single clock cycle, how fast can I clock my CPU? So let's say I have 2 types of instruction, the fast one and the slow one. If I clock based on the fast one, what happens? Can I support the slow instruction? No, right? Because by the time I clock, I lose data already. I haven't finished that. So in that case, the clock will be as fast as the slowest instruction. Now, let's say I have some magic that say I can clock it fast. Then in the middle, once I clock, I save my progress. So I just clock it based on the fastest instruction. The fastest instruction finish in 1 clock, but let's say I have to do a multiply, I just need 3 clocks cycles. Would that be okay? If I can save my progress when I do the multiply, it's okay, right? It's totally okay. So in that case, I can clock faster. What's the benefit then? So let's say this particular CPU, right? Everything takes 1 gigahertz. But for this CPU, every clock cycle is 3 gigahertz. How fast is one add for the top one? Yeah, 3 times faster. If I assume add take 1 cycle for both of them, right? In that case, the first one take 1 nanosecond. My trick is 1 gigahertz. It means that 1 cycle is 1 nanosecond. It's 10 to the 9, and then you divide the whole thing with 10 to the 9, so nanosecond. 3 gigahertz means that 1 cycle is 0.33 nanosecond, so you get 3x speed up when you just do a lot of adds. And in that case, let's say I have to do the multiply the top one, again, 1 nanosecond, so everything is 1 nanosecond, essentially. But the bottom one, let's say multiply take 3 steps. Again, 1 nanosecond, it's not slower, right? So what's my trade-off? Why don't I just do the second bullet point design all the time? I get performance at what cost? So what is the cost here? Any intermediate data in the middle of my multiply, I need to save my progress, right? So I need additional resource to save my progress in the middle. So these become the trade-off of my design. So you can see that in many cases, your, for example, your phone, like a cheaper phone, the chip that goes into simple electronics, they'll clock in a way that's not really fast. Each instruction doesn't go multiple cycles, right? Because they're cheap. I want to make sure I save on the cost to implement these guys versus your CPU. That's a deep pipeline. Usually in one instruction, you go like 30 steps so that you can clock it that way. It's a lot faster. You learn how pipelining works so that you can then realize that this is actually really, really, really fast. So here's some background. We talked about wires already, so I can skip that. Basically, when I draw a straight line, or even things like lines that connect, like something like this, these are wires. Crossing with some number like 4 here means that this wire is 4 bits wide. 4 bits wide. It takes 4 bits. All right. I am not going to draw a lot of diagram because you're not like, you basically, this is a computer science program and I want to focus on just the understanding, right? You're not implementing that for the com art class. Register, you are hopefully familiar with it right now, so I'll skip that. Now, mux, we talked about this already. Mux talked about this already. Clock, we talked about this already. Critical path, we also talked about this. But let's do quick refresher. What determines my critical path? What is a critical path, actually? It has to do with the clock. The slowest set of logic that I need to ensure that I have the output ready, given the input, that becomes your critical path, the longest path in your logic. So the critical path dictates the clock, because if you clock faster than your critical path dictates, you lose data, right? So that determines the clock. Now, combinational logic are a set of logic gates that becomes your compute unit, if you will, adder, subtractor. For example, let's do this. How many people, let's should we try like build the logic to add an 4-bit number? Let's do A3, A0, right? B3, B2, B1, B0. I want to add them together. How do I implement this? All right, how many people are wondering, well, if I want to add something, how do I implement it? Right? And I haven't done this in a long time, so we'll do this together. All right, quickly. All right, so let's say I have all my wiring correctly. I have 4 wires. One of them will be A0, one of it A1, one of it A2, one of it A3. Right, so I can, actually, let's probably simplify things. Let's do 2 bits adding, because the whole thing looks the same. It's just bigger. I don't have room to draw that bit of the design. So I want to add A plus B, and A is A1, A0, B is B1, B0, right? That's my input. And the output side, let's say, is equal C, right? So you have C1 and C0, right? What else do we have when you add 2 numbers together? The carry. All right. So that's my output. All right, for the last digit, how do I add them? We are not optimizing this logic or anything. We just want to say, okay, if I want to do a simple addition, how do I do this? Because there's also a lot of techniques that you can do to make this even faster. But let's add them. All right, so how do I tell what's C0? What's the output of the last bit? XOR, right? And that always will work. Why? I need the odd number of ones on that bit position to have the output of 1, right? So one thing I can do is I put this together and I just XOR them. That becomes my C0, right? We're done at least. Now, how do I determine the carry? You AND them because you need 1 and 1 that will result in the carry, okay? So that's a carry for the last bit. So how do I do it next? What's the next step? I want C1. Can I XOR again? Can I use XOR again? Yeah. I just XOR everything, carry included, right? If I have the odd number of ones, I'll get a 1. Okay, so I can do that. All right, this is gonna look ugly because I didn't plan for where the diagram would go. Now we have C0 and C1, right? What's the last thing that we need? The carry. How do I do the carry? Because it's not as simple as an AND. So basically it's A1 and B1, or A1 and carry, or B1 and carry. I just need 2 of the 1 from all my 3 inputs, right? My input is the A and B and the carry. And as long as I have 2 of these ones, I'm good. So you can do basically, now you have B1 right here. Again, as I said, it's going to look ugly, right? That's my carry right here. So it goes in here. I'll make a quick note here is A1. No, that's B1. This is A1, and this is my carry 0. Carry from the last bit. So this is basically A1 and B1, or like this word, like this V shape is an or, hat is an and, right? So this is basically A1 and carry, or B1 and carry. So that's my logic. I just finished an add 2 bits. You can imagine with n bits, you just keep forwarding this carry all the time. Keep doing this, essentially. For every bit position, there are 3 inputs, A and B, and the carry from the last position. Everything looks the same. Until the last bit, that becomes the carry out. Sometimes we call this the carry out, the output, the carry output. So that's an add logic, right? How's it? It's just build an adder. So you can imagine this is gonna look quite slow if you have to add, for example, 64 bits, right? Why? What becomes my critical path? Whatever carry I have to do, because the 64th bit carry is depending on the 63rd bit, which depends on the 62nd bit, which depends on the like induction, the 0 bit. That's going to be my critical path, right? So as I said, this is not the optimized design in the real CPU. They actually do like, are you in algo already? Algorithm? Okay. Divide and conquer. Anyone heard of that? We split the problem into 2 halves, solve it that way. We can do divide and conquer on our logic to kind of like shorten the time, right? It requires a little bit more logic, but it makes things a lot faster. So that's combinational logic. Anything that has to do with the compute part, right? Question? Where exactly do you divide? So like for let's say you want to do 64 bits, you can subdivide into like the upper 32 bits and the lower 32 bits. The upper 32 bit, as long as you the carry out from the lower 32 bits, you can feed that into upper bit. Then you can keep doing this in half, which would allow you to do the 64-bit division. But you can imagine the wiring, right? It's gonna be quite like a lot of wiring, essentially. But you can basically kind of like subdivide your logic into portions and make sure you kind of parallelize them as much as possible. So that's what we call combinational logic, and that kind of like dictates anything that involves your transformation of your input data into some output. What else are we missing here? So we have a way to compute. What else do we need? We need another set of logic to control and basically progress in time, right? You can't just say that, hey, that's my adder, and it just fixate the input into 2 inputs and that's it. You need to be able to feed multiple input into the same adder, right? So that way you can run a program. You would need, sorry about that, it's called sequential logic. It's a logic that dictates the sequence of your operation. The sequential logic has to do with how do I control the clock? How do I control what goes into my adder? The sequential logic dictates if I have to update the register at the end of my instruction, how do I do that? So that's the sequential logic. So a single cycle processor, let's assume I process everything, it's magic in one cycle, right? So you have AS1, you feed that into some combinational logic like an adder. Then the sequence, you got AS2 as a result. Then you use the sequential logic to store AS2 as a new state. Then you loop. All right. Combinational logic gets you to AS2. Sequential logic saves the progress so that the programmer see the AS2. Then you can resume the whole thing. This becomes kind of like a perpetual, well, I wouldn't call it that, but yeah. Basically, your computer is built from that fundamental way of thinking. All right, any questions so far? Okay. Now, what determines the critical part of our combinational logic is basically the longest part of your diagram. So a single cycle processor, by the way, this is like basically the slowest processor design we used way back in the day. All right, that's when we just invented a computer and we just, okay, let's build it, do the first proof of concept, make sure it works kind of thing. The slowest instruction determine the clock cycle. So let's say, what if some of my instructions have to access the memory? That becomes what dictates how fast my CPU can be. Right? What if it's an I/O instruction? How do I imagine dealing with I/O? Back in the day, I/O memory is kind of like, it's memory unit, same thing, right? You probably don't want something like 1 kilohertz processor, because that's what you're gonna get if you assume every single thing takes one cycle. All right, but let's study how we can build it, because everything builds from here. All right. Side question: how do I measure performance? Yeah. Let's say I run a program. How do I measure my hardware performance? Anyone buy a computer before and like look at benchmark websites? How do they measure the performance? How do they give the score? Mm-hmm. One is the speed. How do we measure speed to do something? Yeah. Right. So somehow we call this wall clock time. Somehow we call it execution time. Sometimes we call this turnaround time. It's a different metric. Three things that I mentioned kind of like serve a slightly different purposes, but it's the measure of time. In the CPU world, when you design a CPU, sometimes you cannot, like, for example, let's say I'm building a simulator right now, and I'm writing, let's say I'm writing a paper that say, hey, this CPU design is better than the current Intel design, right? If I want to run an actual application, that's going to be like trillion of instructions I have to simulate, which likely would mean that every time I run an experiment, it would cost me like 1 month, right? So one thing I can do is I would just take representative portion of the program. For example, if it's a matrix multiply, I'll take out the printf, I'll take out the initialization, I'll just do the actual add multiply, the big loop. And I'll say that's the representative portion of my program because it represents the majority of the execution time. Yes. Yes and no. So basically now I cannot measure the execution time anymore because I don't have the entire program, right? But what I can do is I can measure things like how many cycles does it take to finish this big for loop? Or if I have to run 1 billion instruction, how many cycles does it take? It's still a measurement of time, right? Another alternative is what we call throughput. Given, say, 10 milliseconds, how many instructions can I finish? How many people heard about this metric called flops? Yeah, flops. Yeah, teraflops machine. What does it mean? What does flop mean? Okay, first of all, higher is better. You want higher flops. Flops, FLOP, floating point, FL floating point, OP operation per second. Basically, if I keep doing floating point operation on this hardware, how many can I finish? Why are they important? Because it turns out a lot of scientific applications have to do with floating point. multiply something in the floating point format, add something in the floating point format. So that's why in many hardware, we also measure the flops, right? That's throughput, even the unit of time. Another common one, sometimes we call this IPC, instruction per cycle. Within one clock cycle, how many instructions can I finish? I think you're gonna get at something interesting here. Per cycle, yeah. Huh? Yeah, so usually back in the day, we would use a unit called cycle per instruction to measure like the CPU performance. If I want to finish on average for all the instructions that I run, how many cycles does it take per instruction? It turns out we make the CPU fast enough that now these days in one cycle, we actually finish a ton. So we just flip the denominator and numerator. It becomes instruction per cycle. If you look at CPU, it's actually these days greater than one, usually in most cases. Why are these the case? I mean, I have more transistors. Why don't I just have two adders? So I can do two adds at the same time, right? Why not? Makes sense, right? Given your your technology right now. All right. So what happened in one cycle? Yes. Yeah.
Do you have one standard?
No. The measurement usually okay. One thing you can do is like I just do all the add instruction, right? And say how many cycles does it take for me to finish all this add instruction on average. But a more practical unit would be like I just extract, let's say, matrix multiply and run it on my like matrix multiply as an applicable. I just basically extract representative phase of of a program and feed that to my model of a CPU. Usually through simulation, which is what you guys are doing for project 3. But for project 3, it's simple, one instruction per cycle, always, right? But in a more complicated model, you just run an actual program, like representative phase of an actual program, and we basically measure for every instruction we've seen so far on average, how fast am I? Yeah. And that usually would be good enough to tell how good is your CPU. Then the next step usually is that they will fabricate a test chip, followed by actually crossing the finger, there's no bug on the chip, then run an actual program and see if they actually that fast. And they'll kind of iterate the process to design the next generation of CPU. And it happened for all the chip manufacturers, to be honest, right? To basically keep it faster and faster and faster. I kind of stem from I want to get that as a possible goal. So what happened in one single cycle? Right? Instruction are processed in steps. Recall from not lecture 1, right? Lecture what? Lecture I think 15. Used to be lecture 1 because I just covered this part. Recall that instruction are in the memory. All right. Remember, your program are first in the memory. So the step is I need to fetch the instruction. Keyword that we keep using, fetch, means that I go to the memory and take that instruction. I don't know what they're doing yet. I don't know what's the instruction yet. The next step is I decode the instruction. I have these bits. I now have to figure out what did they do. The next step is if I have to go to any addresses, for example, I have to go to the memory to get my data, I would evaluate the address. Then gather all the operand. Let's say I have to add two numbers, I need to gather the inputs. This is basically preparing the input for my actual instruction. Then the next step, we call it execute, which is execute the instruction. Then we store the result back. And then after this store result back can happen at two places, at the memory or at the register file, right? And at the end, you move the program counter to the next line. Any questions so far? So let's say it's a move instruction that I need to take something from the memory, right? The first thing I have to figure out what's the address that I'm involved with. So that's evaluating the address, because your input can come from the register file or the memory. So basically, make sure I have the inputs ready, evaluate the target address I have to read from, or get the operand from the register file. Now, there's the issue of single cycle, which is what we're going to discuss today, with multi-cycle, which is something that we kind of motivate for the next lecture. For the single cycle processor, everything is done in one clock cycle. The one that you've seen before, I fetch, decode, execute, and somehow write everything back. Multi-cycle, I'll just say one cycle fetch, one cycle to decode, for example, one cycle to execute, one cycle to write back. Which one makes more sense? The first one or the second one? Which one is simpler to design? Obviously the first one. The one that makes more sense is the second one, because I can clock faster. I don't have to wait the entire thing to clock, right? These allow you to, for example, let's say I have an add and a multiply. I can separate out the two commands. If I just do an add, it'll be a few cycles and I'm done. If it's a multiply, a lot more cycles. Let's say if I have to access the memory, it's even worse, right? Because you have to go to cache and blah, blah, blah. That takes a long time. So that way, an add instruction will not be as slow as the memory instruction. And all modern computers are at least built this way and more, way more, all right? No one do single cycle processor anymore. It just doesn't make sense. The next thing is what we call data path versus control logic. So when you process the instruction, right? Again, it's the architectural state 1 to architectural state 2. But in terms of the data you're dealing with, you're basically converting the input data into the output data, all right? It's as simple as that. You're converting the input data D1 into the D1 prime output data. Think of it as a math function. So these are done through what we call the functional unit. It performs the operation on your inputs and you get the output back, right? Instruction would tell what the operation is, and when you process these things, it consists of two components. The first component is the data part. These are the hardware that deal with the transformation of D1 to D1 prime, or the AND or gate to add two things. The storage, for example, the register, these are also the data part. The wire that move things around, also the data part. The control logic means that these are the signal. Think of it as a brain signal to say, hey, do the add, do the multiply, select this wire, select that wire. So that's the control logic. That signal, the control of the data part, enable this, disable this, go here, go here, go there. All right. This would, for example, let's say you want to do add R0, something like this. I want to add R0 and R1 together. Your control logic will go to the register file and say, select R0, select R1. And at the end of the day, when the results come back, select R2 as the target. So that's your control logic to select things. All right. Now, before we go on, let's do a quick 5 to 10 minutes break before we start to draw a simple processor. All right. Now we can start drawing things and try to envision, okay, if I had to build, at least in abstract sense, a functional CPU that's really, really simple, how do I do it? All right. So let's do a quick pause and we will resume around like 11:07. All right. All right. So question for you guys. What do I want from the processor? To actually process an instruction, what do I need? Some ALU, right? Definitely need that. the memory. I need TV to fetch, decode, right? I need a register file. I have to have some way to update program counter. Anything else? These are things that well, at least if I want to draw a simple processor that somewhat high level is still functioning, what do I need? All right, so let's draw them together. Okay. What's the first step when I see an instruction? What's the first step? What do I do? Let's say I have the memory right here, this DRAM. I have my program counter right here. This become an address into my DRAM, right? To access my first line of code, right? So that's fetch. When I finish doing the fetch, the instruction come out. And let's assume I have a decoder. Let's imagine it's like a box that you put in the instruction, it knows exactly what is the instruction and how to control everything. So that it perform an add or multiply based on the instruction specification. All right. Now, I also need the register file, which in many cases, you would specify source 1 and source 2. Right? Basically, you have two inputs from the decoder say, hey, take this as source 1, take this as source 2. R0, R1, for example, right? And that becomes your, for example, your input. But quick question, where else can your input come from? I have an input to ALU. Can I have the input coming from the memory, for example? Right? I can have my data in here, right, from the memory. Now you see the usefulness of the monks soon. Input 1, input 2. So it can come from a register, it can come from a memory. Where else can it coming from? There's a constant inside the instruction, right? Directly from the decoder. You go say, hey, that's number 5, that's input 1, for example. So you can have the mux that have data from the memory as one input, constant from the decoder as another input, and the source from a register file as another potential input, right? Then who pick what input are we using? Again, the first question is, let's say ALU is doing an add right now. It takes 2 inputs to add things, right? And the input can come from your memory, it can come from your register, it can come from your instruction itself as a constant, right? There are 3 inputs here. The decoder knows what the instruction is, so the decoder can also send the select signal. We call this the select signal. Basically, it selects what input are we using. For example, if it's adding from R0 and R1, I would select the input from my register file. Right? Any questions so far? Source 1 and source 2. Yeah, source 1 and source 2. Then for the second input, same, right? You can have input from the memory, from the data, and from the decoder itself, right? It now looks really ugly. Sorry about that. And then you have the select from the decoder, right? I'm not gonna draw it anymore because there's no room to draw this whole thing. There'll be a nicer picture afterward that are in the like diagram format. Okay, but the point is the decoder can now tell where should the input to the ALU is coming from. Is it from the register? Is it from the decoder? Or is it from the memory? Then after this, am I done with the execute? I have an output, right? So for my output, where are the potential destinations? It can be, I can do R0 plus R1, write the result into R2, right? So one of the potential location for my output is going back to the register file, right? Can I go to the memory? Let's say I have some output, I want to write it back to the memory. I can. If I want to, I can also have an output that go into the memory here as well, right? Then the decoder would decide, do I actually enable that wire or not? Or do I disable it? Make sure it doesn't go to the memory. How about a branch? The output should be modifying what? If I jump, what do I modify? Do I modify the register file or do I modify the program counter? You modify the program counter, right? So another location of your output is going to the program counter in case you have a branch or jump. Otherwise, another potential input for your program counter is basically next, we call it next PC, next line in assembly. And then you have a mux here selected by the decoder to select, hey, which one do we use? Do we go to the next line or do we actually jump? All right. So that's it, our simple processor. In a more realistic scenario, there'll be this thing called hardware description language, which you can write. It's a language. Think of it as like a programming, but it's on the hardware that you can write to make sure these boxes behave the way you design it to, and you can build the hardware design based on that. And further on, it basically now become the layout that becomes the actual chip. We have a test chip and run it and like modifying based on some bottleneck that you see and keep going on until you have the full-blown CPU. But this is like a top level super abstract hardware design. All right. So let's do a simple add. Let's say I want to do add R0, R1, and R2. I take R1 and R2, I add them together, write the result back to R0. All right. Based on our design. Okay. Based on our design earlier. So let's say you are using a really simple 16-bit processor with 8 register files. And it's a 3 address machine, so simplify things. I can have source 1, source 2, and destination. What else do we need from the last lecture? Or you need the opcode bit. You need the bit that represents source 1 and source 2 and destination. In this case, each one of them is, because there are 8 registers, so you need 3 bits for each of the source. All right. Then the immediate bit for the constant. And let's remember we're defining our own ISA. So that becomes our toy ISA, the way you designed it. Turn on the microphone. Sorry. All right, it's muted now. So this is similar. Remember how we defined ISA from the last lecture? Same thing here. All right, same thing here. So let's say opcode for the add is 0000011. In this case, right? In this case, you can kind of define your own opcode for each of the instructions, right? Any questions so far? Any questions so far? Yep. So this is like my toy ISA. Remember from last lecture where we designed, like, okay, we want to build a CPU that support 5 instructions. And the opcode is this, register will be in this location, source 2 will be in this location, the same logic here. Because we already did that in the last lecture, let's not focus too much on this design. The same logic. I just pick an opcode for my add, a opcode for subtract or whatever, right? And this bit will go to source 1, this bit will go to source 2, this bit go to immediate. And each row here depend on the format. The compute, the first line is like when I have two source from the register. The second line is source 1 from the register, source 2 from my instruction itself as a constant. Load store immediate means that I want to basically put this constant into the register. Load store relative, my bad. Put this constant from the memory. I use immediate as an address. Take that address location, put that value in the register. Relative means I have the base register plus immediate. And then the jump basically go to that instruction specified by the immediate. All right. Now here's the visualization of the same thing I draw earlier. The blue thing is the decoder. That design, I took the instruction in. Then based on the instruction, the 16-bit instruction that you see, it sends out the control signal, right? So let's say I want to do an add, right? This becomes the program counter's address. And let's say you see the add R0, R1, and R2 here, right? Basically, this means I want to do R1 plus R2, write the result to R0, right? With me so far. So basically, that's the instruction I'm pointing to. Huh? Okay, good. At least physically. All right. So the program counter, let's say it points to the instruction is basically an add. I want to do R1 plus R2 as an input, right to R0. All right, that's our assumption. With me so far with this assumption. All right, instruction in the memory, the orange thing, the orange box, that's my memory. I point to that location, I see the instruction. The instruction is now being fetched into the decoder. All right, the decoder then understand I'm adding. So the first thing is enable the adder here and make sure the adder takes the right input. So what are the right input in our case? What are the input 1 and what's the input 2? Add takes 2 input. So what are the 2 inputs? R1 and R2, right? So in that case, the decoder also know, okay, I need to take R1, I need to take R2. Remember the gather the operand step from earlier, right? Now the decoder say, okay, I need R1 and R2. So it sends the signal, the select signal to the register file to select in a way that R1 and R2 are being passed here. So it selects from the register file and make sure it also selects the input that comes from the register file to forward, basically to forward R1 into source 1, R2 into source 2 of my adder. All right, with me so far. Again, the decoder job that's doing this. Your project 3 is basically involved making sure the decoder do the right thing based on the bit you see. What's the source 1, what's the source 2, make sure it's there. All right. Then the next step is I have R1, I have R2. What do we do next? Add them together. Result coming out here, right? The results are coming out here. So what do I write to? I have R1 plus R2. Where's my destination? R0, right? So the data goes in here. Decoder, this guy, then select here, right? I know if the wiring is odd, it's go to select that the output from my ALU, take it and feed it in here as R0. Select R0 as a destination, make sure it's passed through from your adder. Now, that's it. The next step is what? I am done the adding. R0 has the updated value. What's the next step? What's the last step here? Update the program counter, because if we do not update the program counter, you stuck here at R0, R1, R2 forever. So the next step is select, and I want this guy, program counter +4, which is the next line, maybe +2. My bad. Because each instruction is 16 bits. Each instruction is 16 bits. The next line is going to be program counter +2 more bytes. All right, +2 more bytes. That becomes the next PC, the next program counter. There will be a a lot of hints into how do you implement Project 3. You have to figure out what's the next PC based on your instruction. What's source 1, what's source 2, what are the ALU that you have to run? Is it an add? Is it a multiply? Is it a division? Blah, blah, blah. Is it a jump? Is it a branch? And you make sure you update the correct thing based on what you saw. All right. Any question? Kind of with me so far? Are you guys kind of with me so far? Yes, no? Kind of. How many people kind of understand the high level but still have the question, how do I actually implement this in detail in hardware? Good. I want you to leave it that way. All right? Because you're not learning circuit. That we can't go there yet. Otherwise, we need a lot more lectures to like, okay, for this wiring, how does MUX work? And well, we talked briefly how MUX works, right? But the hardware implementation, totally different class. All right. But with me so far on, let's say I have an instruction, this is what's gonna happen. Congratulations, you have a CPU. A really slow CPU, by the way. It's only 16-bit, not a lot of support, but running. All right. Now, I do have each slide to do individual steps, but I decided to draw everything on the first slide. All right. So I'm gonna skip over and go back to the question of single cycle versus multi-cycle. Because what you saw earlier in the single cycle processor, everything we said so far has to happen in one cycle. You can imagine the clock is going to be really slow. Why? The whole process has to finish before you can clock, right? The whole process until you update the program counter has to finish before you can update the clock. And that's your process 3, by the way. Multi-cycle processor means that I want to be able to go to the next cycle, clock it such that, for example, let's say I just do an add. It means that when I have the input ready for my adder, it only takes one cycle, for example. But if I have to do a multiply, let's say I have the 2 inputs ready, fed to the multiply, I'll need to make sure that I wait at least 3 cycles to finish the multiply. And every time I clock, I save the internal state of my multiplication. All right. But this allows me to clock a lot faster, which means that if I have a lot of add instructions, the program gets faster quickly. Right. This is what we call decoupling latency of the control signal from the data path. The data path, for example, the add and the multiply, take a different amount of time. I just want to make sure I clock it so that I can give the control signal to do the right thing all the time. But the clock is basically handling the control while the data path can do whatever they want. All right. We'll go into more detail when we go through pipelining. With multi-cycle processor, right? So again, when you look at how to process the instruction, same thing here. Fetch. Decode. Once you decode, you gather the input, execute, then you write the result, then you move to the next instruction. All right. Then you move to the next instruction. So let's go back to our toy example and let's assume, for example, the memory take 1 cycle, decoding take 1 cycle, update register, both the program counter and register file take 1 cycle, and every single ALU, add, multiply, whatever, take 1 cycle. All right. Let's do multi-cycle architecture where each of these steps take 1 cycle. Okay, so that we can highlight some benefits. Now, Let's say I want to add R0 and R1 and write the result into R2. I just want to do a simple add instruction here, right? How many cycles does it take? Fetch, right? Plus 1. After I fetch, decode, one more cycle. Okay. After I decode, I need to gather the operand and add, right? So this is one cycle to gather the operand from register file and add things together. Then update everything here, one cycle. And I can also update this, but we can do it in parallel because I can update program counter at the same time as update the results. So this can take, for example, 4 cycles to finish. Right? Each of the steps that you solve through your design will take one cycle, one cycle, one cycle, one cycle. Now, let's say I have to do a multiply. Again, the same thing, right? Fetch, decode, execute, and then write the result back to both the program counter and the register file. Again, 4 cycles. Right? So you can see that if we have first of all the magic memory and magic adder, magic multiplier, everything takes the same amount of time. In this case, everything is 4 cycles, right? Is the world behaving this way? No. All right. So let's say we have to load a value, and now let's say memory. And let's assume it hit in the L1 cache. All right. Let's assume your data is already in the L1 cache. Usually it is about 4 cycles. Fetch. How many cycles do I take? Fetch. It take long because I go to the memory. I said I assume I hit in cache. So 4 cycles. Right? Decode. What's the instruction? I want to go back to the memory because I need the data. Right? Plus 4. And then plus 1 here to update the register, right? So how many total? 10 cycles. Now, let's assume the same assumption. Any memory request takes 4 cycles, all right? But let's say I have to do an add. How many cycles do I take? Fetch, 4. Decode 1. ALU 1, update 1. So that's 7, right? So with multi-cycle processor, one thing you can see clearly is now add is faster than a load, right? Now let's assume, let's say a multiply takes 5 cycles, add takes 1 cycle. In this case, multiply will be 11 cycles, right? So you can see now each operation will take a different amount of time, and I can clock a lot faster this way, all right? So that's the benefit of multi-cycle architecture. Okay, so let's say you have to do all of this thing, right? And have the magic 1 cycle memory. This would take 4, 4, 4, and 4. It just happened you follow diagram, everything is take the same thing. Now it is not not magic. Let's say multiply. The ALU for the multiply take 5 instead of 1 cycle. The load, if I have to go to the memory, I have to take 10 cycles. Let's say it has to go to the level 2 cache. L2 cache usually is 10 to 11 cycle. You can see that the set of 4 instructions, right, becomes this. The first add is 4 cycle, but everything is the same. Oh my bad. Sorry, you have to access the memory. I forgot. So you first fetch, you go to the memory, so that's 10 cycle. Then 3 more cycle, decode, add, and store result back, right? So the first add is 13 cycle. Multiply, you go to the memory 10 cycle, then you do decode 1 more, multiply 5 more. Then you write it back to the register, right? So it's 10 plus 1 plus 5 plus 1. that's 17. XOR is 13, the same as add. Load means I have to go to the memory twice. So that becomes 22 cycle, right? Now, my quick question is, can we do better? First of all, this kind of seems slow, right? Because I cannot even start fetching the multiply until I finish the first add. But let's say I'm trying to finish up the add. Is anyone using the fetch logic? No. So can I start the fetch for the multiply at an earlier cycle when I'm done with the fetch logic, when I'm doing an add? Yeah. Quick analogy. How many people have to wash that clothes? Like clean, like let's say you have to, how many people have to do laundry on your own? All right. How do you do it? Throw in the washing machine, then throw in a dryer or hang it dry and then fold it back, right? Let's assume that you're working on my quiz and you haven't like do laundry at all, because that's your life. And now you have pile of dirty clothes, right? That doesn't fit a single wash cycle. What do? You split. First of all, you split. Then you wash the first batch. Once the first batch is done, you move the first batch to the dryer. The washing machine, is anyone using it? Well, assume your friends are like not as messed up as you are. All right. So then you have the washing machine up to you. So you throw the second batch in while the first batch is in the drying machine. Right? We call this pipelining. Work the same way here. I finish fetching the add. The fetch unit is empty. It's not doing anything. So let's fetch the multiply. Then the add go to the execute stage, dealing with the ALU. The multiply go into the decode stage, trying to figure out, hey, it's a multiply. The third instruction, XOR, comes in and use the fetch unit. So that's what we're gonna cover next on Thursday. We call this pipelining. The second thing is you might have realized that if I have an adder, if I have a multiplier, I can do two instructions at the same time, right? Because when I'm adding, my multiply unit is empty, it's not doing anything. So that's also a technique called superscalar that handle that as well. You can now issue the add and multiply in parallel for modern CPU. All right. We will cover pipelining for this course. We will not cover superscalar that we cover in Comarch, but here are some of the basic things that have been done to make your program faster. All right. So that's a wrap for today. I have a quick in-class exercise, which basically asks you to, if you don't have to write any assembly yet, just make sure you install the simulator called SPAM. Yes. So your project has to do with the MIPS simulator. MIPS is an ISA that is used back in the day. It's a reduced instruction set architecture. It doesn't support a lot of instruction, but it's actually really, really powerful. This SIM, which is MIPS written backward, is a simulator that allows you to write MIPS assembly, and it simulates an actual CPU that would run MIPS and would show once you run your program, these are what would happen to each of the register file. So you can use this to double check the correctness of your solution. You can also use this to generate the input for your tester, your own tester for the lab. All right. The starter code also has some basic tester, but I have my own way bigger test bench to test your submission. All right. For this project, we don't do milestone because once you, to be honest, once you figure out what you have to do, the rest are a giant if else and switch case. So I can do milestone 1, which is finish the first add instruction, then milestone 2 is finish the rest. Again, for the project, we basically push everything to the last day of class. The deadline I put in for the submit before, that's like available until don't submit after that date. All right. I think it's the 17th. That's absolutely, yeah. Because the last day of class is 14th. All right. Final week is the week after. The final, I plan to do it on the last day of class, which should be the 13th. Is it Thursday? Oh yeah, I forgot. Yeah, for you guys, there was SysSkill, my bad. SysSkill will happen on the 14th. For you guys, I'll do like a makeup class on Friday, online exam again, unless you want to have depend online or offline. Let's do a quick vote here.
Make it shorter, please.
Online shorter. Okay, got it. I promise I'll you on that. That's not a big promise though, to be honest. Quiz 2 is long. Yeah, exam, shorter exam. All right, still again, 48 hours online. The same deal released on Friday morning, like 12:01 a.m. like first minute after midnight on Thursday. What? Why? You pick your time. Do you want to work on it? Should I just do it in the morning? I mean, I don't mind. I can do like 10 a.m. Yeah, I think it's the same, right? So, and then I'll schedule a makeup class. I'll be here. You can drop by and say hi. And then we will probably do the demo for the project 1 and 2 in the final week. All right. Project 3, I have a grading script, so I don't need a demo. I just like run my own test and destroy your implementation. All right, so okay, so there's a question online, what's happening after midnight on Friday, the last week of the semester, last week of lecture week. I will release the exam for quiz 3. You have the same deal, 2 days, 48 hours to work on it.